problem 134 from chapter 16. In this problem, block A, which is attached to a cord, moves along the slot of a horizontal forked rod. At the instant shown, the cord is pulled down through the hole at O with an acceleration of 4 meters per second squared, and its velocity is 2 meters per second. Determine the acceleration of the block at this instant. So we want to find the acceleration of the block. That's A. The rod rotates about point O with a constant angular velocity of 4 radians per second. They drew the little XY coordinate system here. So we're going to use that. That coordinate system is rotating with the rod. And so the angular velocity of the coordinate system, capital Omega, is the same as the angular velocity of the rod, which is 4 radians per second, rotating this way, which would be in the positive k hat direction. And they said it was a constant angular velocity, so that means the angular acceleration of that coordinate system is 0. And if the cord is being pulled with a speed of 2 meters per second, if you're standing at point O, rotating with the rod, you would see the block moving towards you in the negative I hat direction. So you are looking at the velocity of block A standing at point O in the rotating coordinate system. It's coming towards you, that's in the negative I hat direction, at 2 meters per second. The acceleration of the cord gives you the acceleration that you would see if you're standing at point O rotating with the coordinate system, and that is also in the negative I hat direction. Okay, so I think that's everything that they give us. Oh, we also have this 100 meters here, which will be important when we look for the position vector. Okay, now look at equation 16, 29. We're looking for the velocity of block A. So all the subscript B's are going to change to A's, and we have the origin of our coordinate system at point O. So all the subscript A's are going to change to O's. And now that we have our full equation written out here, we can cross some things out. So point O is not translating. The acceleration of point O is 0. The angular acceleration of the coordinate system is 0. So this term is 0. Okay, now we can start calculating some things. Let's actually do the cross products before we plug things into the equation. So for this here, now we looked at this in the last problem. When you compare this to equation 16, 18, we have negative omega squared times RB. Whenever this position vector is perpendicular to the angular velocity, it's always going to turn out this way. So if you do two cross products and you have these two vectors are the same, if this vector is perpendicular to this vector, it's always going to turn out that way. And are the vectors perpendicular in this case? The position vector, which goes to point A from point O, that would be like this, has a length of 100 and is pointing in the I hat direction. So this should give me negative omega squared. What's omega? 4 radians per second. So this should give me 4 radians per second squared. And position of A with respect to O is in the I hat direction. Okay, so without actually doing the cross product, just by comparing to what we had in equation 18, I think I should get this. So let's check and make sure that it works. So I first do, let's leave the units out here for now. So that's 4k hat crossed with 4k hat crossed with this vector is 100 in the I hat direction. When I do k hat crossed with I hat, k hat crossed with I hat gives me j hat. So now I have 4k hat crossed with 400 j hat. K hat crossed with j hat gives me negative I hat. So this is negative 1600 I hat. Does that agree with what I have here? Yes, it does. Okay, and so if I put the units back in, that would be 1600 meters per second squared in the I hat direction, which makes sense because this is going to give me an acceleration, so it should be in meters per second squared. Okay, now let's do this cross product here. And this is 2 times omega, so that would be 8 radians per second in the k hat direction, crossed with my relative velocity, which is negative 2 meters per second in the I hat direction. K hat crossed with I hat gives me j hat. I have the negative sign here. That's negative 16. The units are meters per second squared. J hat. Okay, so now I'm going to take this whole equation and look at what I have. This gave me negative 1600 meters per second squared in the I hat direction. This gave me minus 16 meters per second squared in the j hat direction, and I have to add my relative acceleration, which is minus 4 meters per second squared in the I hat direction. Well, I have I hat and I hat. This was 100 millimeters. That wasn't 100 meters. Okay, so I got to go back and fix that. This is 100 millimeters, which means 100 millimeters, this would be 0.1 meters. So this would be 0.1 meters. So I should move the decimal place over 3 places. So this should be 1.6. So that's 0.1. And this would be 0.4, and that would be 1.6. So this is 1.6. Okay, now I can add the two I hat terms together, and I have minus 1.6 minus 4. That gives me minus 5.6. That's in the I hat direction. I'm going to put the units at the end. The units are meters per second squared, and the j hat term is negative 16. Okay, so that concludes problem 134. We used the same equation as we saw in the previous problem, and once again, point A is not translating at all, and the angular acceleration of the rotating coordinate system is 0, so the first two terms canceled out.